So these four factors and the three parts of the collision theory. So give me one of the four factors that increase the rate of reaction. Say again?
Increase the temperature.
Temp. Okay, so we can increase the temp. And what part of the collision theory is that responsible for?
Energy.
Okay, so the reactants have increased energy. What's that energy used for?
Collide them or to I'm not sure. To start the other, give energy to the next reaction.
No, that's the output. When two things are going to react with each other, what do they have to do first to themselves? Say again?
Break apart.
Yeah. So that initial energy is used to break the chemical bonds that they already have away from each other. So then they can disassemble the atoms and then reform with the new atoms. Okay, do we have another factor? Increase the temp. What else can you do to make it go faster? Add a catalyst. And what's that going to do for you?
That will speed up the reaction. So that would probably have something to do with their energy also.
No. Yeah, it orients. So the three things for that collision theory where they have to hit with enough energy and they have to hit with the correct orientation. And the catalyst sets them up so they can hit with the correct orientation. Remember we talked about the catalytic converter in the car? So what we're trying to do is get the things to align, and those nitrogen monoxide molecules, the NOs, when they're flying through three-dimensional space, they're a lot less likely to run into each other than if they're sliding down the surface. And so because they're sliding down the surface, going down that little tube, they're more likely to run into each other correctly, where the N's run into each other and the O's run into each other, then they can let go of each other and then form the nitrogen bonds and the oxygen bonds. Okay. Got two more.
Concentration.
Okay.
Of the reaction. Of the reactants.
So if I increase the concentration, what are they more likely to do? They're just simply more likely to collide. And the last one?
The nature of the reactant, solid, gas, liquid, aqueous.
So if my reactants are solids, they're less likely to run into each other than if they're gases. So it's literally just about colliding. So if I take something that's a solid and I dissolve it in water and make it aqueous, then the components are more likely to run into each other than if they're just sitting there as a solid. All right, what do we have for catalyst requirements? Got to do two things.
Has to speed up the reaction and not be used up.
It's got to be, you have to have exactly the same amount when you're finished as when you started. And it's got to make the thing go faster. A reaction progress diagram. So this axis is energy, and this axis is time. And here are my reactants. Here are my products. Here's my change in free energy. This is my activation energy. And then this area up here is the transition state. Okay, what's the activation energy being used to do? Start the reaction, but when we say start the reaction, what do we specifically mean? On like the molecule size level. When I put the match on the piece of paper to get the match going, what is the energy from the match being used to do?
Break.
To break the initial bonds. So if we're talking about a piece of paper, we're talking about glucose. And so I'm separating the carbon-oxygen, carbon-hydrogen bonds initially. And so then that process gives enough energy to start the next glucose molecule to separate out. But that activation energy is to break the bonds initially. So if we're looking at this first question, when you're putting the match on there, you're increasing the temperature so that those molecules have enough energy to break their own bonds. And then the reaction can proceed as you go forward. And the delta G, what's that? Change in what? Free energy. So what is happening in this reaction? It's gaining energy. So is this a spontaneous or non-spontaneous reaction, right? So this reaction would only happen if you were constantly inputting energy into it. The moment you stopped adding energy, it would immediately stop. And the transition state. What's going on in that transition state? So we had an example of a reaction in the notes where there was hydrogen gas and chlorine gas. And they were going to come together to form hydrochloric acid. And the first thing that needs to happen is the hydrogens need to let go and the chlorines need to let go of each other. And so for a short period of time, I'm in this situation right here. Is anybody happy? Everybody's very dissatisfied with their current situation, right? Nobody has energy levels, electron configurations that look like any noble gases. Everybody's upset. That is your transition state. So the transition state is when the atoms are transitioning from one stable state to another stable state. So they're very unstable during that portion of the reaction. All right, so we want to get the orders for this reaction. Which trials would you like to start with? Okay, so if I do 1 and 2, the concentration of A goes up by 2, and B doesn't change at all. So any changes in my rate are solely due to what? A. And how much does my rate go up? This goes up by a factor of 2. Okay, so for A, when I double A, I get a doubling of the rate. So what exponent controls A? A 1. Okay, so B rate. All right, so which trials do you want to do now? 1 and 3? So when I go from 1 to 3, I get no change there. I get a doubling there. And what happens here? Goes up by 4. So my rate went up by 4, but I only changed B's concentration by 2. So what exponent controls B? By 2. So to answer this question, you would say that it is first order with respect to A and second order with respect to B. All right, let's do that same thing with the next one. All right, so let's choose trials 1 and 2 again. So there's no change in B, and how much does A go up? Goes up by 1.5, 1.5. And how much does the rate go up? It also goes up by 1.5. So A goes up by 1.5, the rate goes up by 1.5, so then it must be a 1 first order with respect to A again. And then let's do trials 1 and 3. So I got no change in A. How much does B go up? Three times? So B goes up by 3. And then how much does my rate go up? Is that?
0.038.
Okay. So I'm giving you this one because the numbers that we've done up to this point, sorry.
10.0.
Oh, 10.03, okay. So the numbers that we've gotten so far, they've been very crisp and clean. Like, I increased this by 2, it went up by 2. I increased this by 2, it went up by 4. Increased this by 3, it went up by 9. Exactly. That's just not the way it's gonna look like in lab. So we're gonna do a lab like this, and it's gonna be, oh, I doubled the concentration here and it went up by 0.87. So what do you think? So this goes, I changed B's concentration by 3 and the rate went up to 10-ish. Close to 2? We okay with that? What happens if this is a 2? What rate do I get? I get 9. That's the answer. Second order for this one.
Just get as close as you can.
Just nice whole number, as close as you can. It'll run off of whole numbers, but your answer might not be exactly fit right on top of that whole number simply because somebody did the experiment and maybe they didn't clean their glassware perfectly. Maybe there was some contamination for some other substance in there. Yeah.
So if it was closer to 3 cubed?
If it was like 27 or something like that,
maybe
yes.
0. Yeah.
Yeah,
Right,
absolutely.
agree.
So like if this jump here from the 0.26 to the 2.61 would have been, say, 30,
Uh-huh.
then you would have thought it was third order.
Okay, and if it was lower, like 25?
Probably still 30, because that's a lot closer than it is to the 9.
Okay.
Okay, so for this one, the answer is going to be first order with respect to A and second order with respect to B.